Okay, thank you. So I'm going to talk about autonomous driving, about reinforcement learning for driving policy. This is a joint work with Shaked Shama and Amnon Shashua. So let me start with a demonstration of the current state of autonomous driving. So this is the cars that I use to drive every day. I'm taking, using my cell phone, I'm filming this video while the car drives itself. It's the road from Jerusalem to Tel Aviv. You can see that I have a screen here that shows the detection using a single camera of lanes and other cars. And it's a nice highway situation where the car knows how to keep its lane and have a safe distance from other cars. You see here that it is raining. This is still fine. Anyway, you get the picture. This is where we are now. But there is a problem with the approach, and we need another component. The problem is that driving is a multi-agent game, and there is in the current technology there is a key flaw. And this is an article about what is the glitch. The glitch is, you can see down here that the autonomous cars nowadays obey the law all the time. Okay, and it's okay for a highway scenario where there is no high density of cars, but good luck trying to merge onto a chaotic, jam-packed highway with traffic flying along well above the speed limit. It tends not to work out well. So I want to demonstrate this is where we want to be. Okay, you heard the noise, it's a part of the effect. This is just a junction in Napoli. You see that cars come from every direction, pedestrians walk around, and cars must push their way into the junction. Otherwise, if they will be very passive, they will just stay in place and will not make any progress. Okay, another demonstration. I will run forward a little bit. This is Arc de Triomphe in Paris. You see the amount of cars that want to cross this roundabout, and they are all packed together, and you need to push your way to arrive to the other side. So let's continue to something more challenging. You can probably guess where it is. Okay, a junction in India. Now go figure out what's going on here, but traffic goes and everyone is in place. So this is where we want to be. And what I'm going to talk today, what is a missing component from moving from a nice highway driving into crazy situations and junctions and roundabouts. So in general, we can decompose the autonomous driving task into the part of sensing. So we have sensors, cameras, radars, maybe other sensors. We have a map knowing the environment around, and all of this goes into a sensing. And sensing is a process of understanding the present. And so far, the main focus of autonomous driving was on sensing, on understanding the present. The output of the sensing module is a sensing state which describes the world around us, lanes, cars, pedestrians, traffic lights, etc. Then comes another module, which we call it a driving policy module. The driving policy module is responsible for planning for the future. It is a reasoning of what will happen if I will do something. And the output is a desired trajectory where we want to be in the next second. Then finally there is a control module that actually is responsible on giving commands to the engine and to the steering column in order to fulfill the desired trajectory. So I'm going to focus today on the driving policy module. We're going to use machine learning for autonomous driving. In sensing, we have a single correct answer is there a car here or not? The predictions that we make do not affect the environment. The loss function is immediate. So all of this brings us to supervised learning problem. This is well understood, and we had a lot of work on understanding the scene and the sensing state using supervised learning. In driving policy, there are many possible correct answers. There are many different maneuvers that we can make, and all of them are correct. The actions that we make affect the environment, and we have the credit assignment problem, meaning that actions that we do now have long-term effect, and we do not really know to put the finger on when we did something wrong. So all of this calls for reinforcement learning. Why do we need machine learning for driving policy? I think in this audience it is pretty obvious, but maybe the main reasons are we want something generic that will hold for many possible scenarios, not just for a specific route. And there is a complicated decision making to have, like understanding the intention of other agents, the trade-off between being defensive or aggressive. We need to negotiate with other drivers, and in a sense we need to understand or to figure out the rules of breaking the rules, because nobody here is driving by the rules as they written in the law. Okay, if you will do it in dense traffic, you will stay in place. You must know what is legitimate and how you can break the rules. Okay, so what I'm going to talk about is the first part. We'll talk about reinforcement learning without Markovian assumptions, and I will explain what is this Markovian assumption and why we don't like it at all, and why we want to do something without this assumption at all. Then the second component is about safe reinforcement learning. So there is a generic problem with learning, with machine learning. Machine learning most of the time talks about expectations. So we take average performance, and this is our measure of how successful is the output of the machine learning technology. This is fine most of the time, but it can be very problematic in driving scenarios where one mistake that is very, very rare can cause an accident, and you don't want accidents at all. So you want a reinforcement learning that will deal with some guarantees that are worst case guarantees and not guarantees on the average performance. So I will talk about it in the context of reinforcement learning. And at the end, I will talk about an options graph, a model of decomposing the driving policy model into semantically meaningful components, which helps us to build a successful driving policy in a very efficient way. Okay, so what is reinforcement learning? Our goal is to learn a policy. A policy is a mapping from a state space to action space. In our case, we can think about the state space as something that describes all the environment, and the actions are either the commands to the engine or the desired trajectory that we want to drive in the short range. Reinforcement learning is like a game. The game starts at times 0 and progress at every timestamp. The agent observes the state, S sub t, then it needs to decide on an action AT based on a policy which is a mapping from the state space into a distribution over the action space. The environment moves the agent to the next state, and this goes on. And there is a feedback for learning, a reward signal that assesses the intermediate quality of every timestamp. Now, in the literature, the most commonly used model for reinforcement learning is a Markov decision process model. And beyond what I described about reinforcement learning before, the Markovian assumption is that the next state and the intermediate reward are conditionally independent on the past if we know the current state and the current action. So once we know the current state and the current action, we can forget about all the past. And there are very nice mathematical consequences of this model. So if our goal is to maximize to maximize the sum or discounted sum of the regret, we can summarize all the future rewards into a single number, which is called the value function. So V of S sub t is the expected future reward if we are now at state st at time t. And similarly, there is the famous Q function that takes the state and the current state and the current action and decouples or summarizes all the future. Suppose that we are at state st and we are taking action at at time t. So it's nice to summarize all the future into a single number. There is also a dynamic programming consequence of the Markovity, which is known as the Bellman equation, and we can solve the Bellman equation and come up with the optimal policy. And another consequence of the Markovity is that the optimal policy is actually a deterministic policy that is defined based on the current state, and it is just the greedy policy with respect to the optimal Q function. So all of these are very nice consequences of Markov decision processes. And if we think about a very rough taxonomy of reinforcement learning methods, there are roughly 4 families of algorithms. One algorithm is learning by imitation, where we just observe pairs of state and action that where the action was chosen by some good agent. In driving policy, it can be human, and we learn by supervised learning the mapping from the state to the action. This is very nice because it is supervised, but the problem is that errors propagate and accumulate, and the end result policy is not very good. Another approach is a direct policy optimization approach where we express the policy in some parametric form and directly optimize it using some gradient algorithm. There are other families like value-based learning where you want to learn either the Q function or the value function, and model-based learning in which you learn the actual generative model of the environment. What is the next state given the current state and the current action, and once you know it, you end up with an optimization problem of planning, finding the optimal Q. And in practice, combination of the different methods often works the best. All of this is about Markov decision processes, and I recall that Markov decision processes assume that the current state is conditionally independent of the past given the next state is conditionally independent of the past given the current state and the current action. But this assumption is wrong and is really problematic for driving. And the simple reason is that driving is a multi-agent scenario. We are not alone in the world. It's not like a robotic scenario where you want to move an arm of a robot, whereas a robot is alone in the room and that's it. In driving, we need to react to other agents. Now, for the Markovian assumption to hold in a multi-agent scenario, we need that the state that represents the present, or even if we are talking about hidden state, like in partially observed Markov decision process, in any case, the state should decouple all the past. So it should contain things like the mood of the other drivers, okay? Because the mood of the other drivers is something that you can infer from the past actions of the other driver, and if this is not part of your state, that it's not true that the future is independent of the past, given your state. Okay, and for this reason, we do not want to assume Markovity at all, but still we want to find a policy which is a function of the state and maps into the action. So in fact, we're talking about an agnostic reinforcement learning setting. The optimal policy is not necessarily only a function of the state, but we are fine with finding the best-in-class policy that depends only on the state. But a consequence of it is that we cannot rely on the value function because the mere definitions of the value and the Q function are meaningless without the Markovian assumption.
When you say state, you mean the state of the individual or the state of the system?
The state of the system. The state of the system can contain all the cars as well as internal that you want to remember for the state. Okay, so getting back to the common methods for reinforcement learning, now let's think about which methods are adequate if we do not want to assume Markovity. So obviously, value-based learning is not adequate because the value function is not well defined anymore. Also, the model-based learning plus planning is not a good thing because the mere idea of model-based learning is to learn the next state given the current state in action, but now the next state is not a function of just the current state in action. Imitation learning, on the other hand, works seamlessly because we just want to mimic a human driver or some good agent. So there are no assumptions on the dynamics of the system whatsoever. What about direct policy optimization? So I'm going to show you that direct policy optimization, some of the methods in direct policy optimization, in fact, do not assume Markovity at all and can work without Markovian assumptions. So let me be more precise about direct policy optimization. The objective of reinforcement learning is to maximize the expected reward. So we have S bar be a trajectory or some sequence of state and action, S1, A1, S2, A2, etc. And R of S bar is an arbitrary function which assesses the total quality of a sequence. Now what we want to do is to maximize the quality of sequences, and the optimization is over our decision making, our policy pi. And the objective is the expected value of the quality of sequences where expectation is with respect to the randomness, and the randomness is both randomness of the environment, which we do not want to model, and we do not want to make any assumption on the randomness of the environment, but it also depends on pi, on our policy. So our policy can be stochastic, and then we have randomness in our decision making. So this is our goal. And what I'm going to show you is that policy stochastic gradient can work without Markovian assumption. So we're going to talk about a hypothesis class of some stochastic policies, which I denote by pi theta. So we want to learn the parameter theta. And it is a stochastic policy because for every state, the sum over actions of pi theta of A equals 1. So now assume that pi theta is differentiable with respect to theta, and this will be the case if we are using deep networks for modeling the policy function. And we can express the probability of sequences over sequences with respect to theta by p theta of S bar. And we assume in this probability that our actions are chosen according to pi theta, but we make no assumptions on how the states are chosen. Okay, so in particular, we make no Markovian assumptions. So the learning problem becomes finding the best parameters theta to optimize the expected value of the reward of S bar, where expectation of S bar is with respect to P of theta. Okay? So this is the problem that we want to maximize, and the question, can we maximize it directly? And the answer is yes. We can maximize it directly using stochastic gradient descent. And this lemma here gives us a very simple way to come out with an unbiased estimate of the gradient of this objective. And this is a bit surprising if you haven't seen it before, because we are taking a derivative of a very strange objective. So the dependence of the objective on theta is through the expectation over sequences using this P of theta, which is a long sequence of a product of probabilities. Nevertheless, if we randomly sample a sequence based on our theta by just driving according to the actions induced by pi theta, and then set het of nabla to be this expression here, then the expected value of het of nabla is exactly what we want. It's the gradient of the objective of this optimization problem. Okay? And this lemma is correct So this expression is not new. It was known before as a policy gradient theorem, some variants of the policy gradient theorem, but it is true even without making any assumptions on Markovity of the problem.
But you decoupled the log into sums, so you assume some sort of independence.
No, there are no assumption on independence here at all. The only assumption of independence is that your action, AT, only depends on ST via pi theta. But you don't make any assumption on ST plus 1. You don't make the assumption that ST plus 1 only depends on ST and AT. It can depend on the entire past. Okay? Yes?
You gain from being stochastic?
Yes, here I gain from being stochastic because if I want, without stochasticity of my policy, this expression would have been 0 all the time.
Could you explain the relation between p theta and pi theta?
Yes, p theta, I will tell you exactly what it is. So the environment decide on S1 by some stochastic law. Okay, so there is a probability that the environment will choose S1. Then we choose A1 using pi theta. So we sample A1 according to pi theta A1 given S1. Now the environment picks S2, and the environment can look, okay, at the entire past. So even at time t, ST plus 1 is chosen on the entire past. It depends somehow on theta because we chose the past contains our actions that are depend on theta, but not in the derivative. Exactly. This is a trick. Okay. Exactly. Okay. So I will go a little bit quicker. There is a big issue of variance. So we got an unbiased expression of the gradient. But what about the variance? The variance is very important in the convergence rate of stochastic gradient algorithms. So we need to pay attention to the variance. So here is a lemma showing a generic way of reducing the variance of this estimator. So again, this lemma is not by itself. The expression is similar to things that are that exist in the literature, but the new thing here is that the specific expressions are tailored to the non-Markovian setting, and this lemma holds without any assumptions on the environment. Okay, so now we have two methods that work without the Markovian assumptions. One is imitation learning, and the other one is direct policy optimization. And we can combine these two approaches, and this is exactly what we are doing. We initialize pi theta by imitation learning, by imitating a human driver, and then we continue to optimize pi theta using stochastic gradient with our policy gradient without making any additional assumptions. And I would like to show you first result. So the agent here is a white car, and it should learn to overtake to push its way into an overtake. And as you can see, even though it looks very scary, it managed to push its way and perform the overtake. However, if you will enter this car, it will be a bit scary. So look again, we make no accidents, but it is close, okay? And this brings me to the second topic about safe reinforcement learning. So on expectation, the learned behavior of this car was very, very good, but with some low probability, it made accidents. You wouldn't want to enter this car. Okay, so there is a challenge here, because the objective of reinforcement learning is to maximize the expected reward. So we want to maximize the expected value of the quality of a sequence. So suppose that this assessment of sequences is between -1 and 1 for typical events. So for example, a good reward of 1 for successful change of lane, and -1 for we didn't make the overtake correctly. But the policy is very good, but with a very low probability it performs an accident. Say P equals 10 to the -8. Okay? Now what would be the effect of this low probability of an accident on our objective? The effect would be very, very small unless we make the reward of an accident event very, very high. So if we wanted to have any effect, we want that the product between the probability of accident and the negative reward of accident would be order of 1. Okay, so we need a huge value to pay a lot for an accident. But if we pay a lot for accidents, the variance of our estimators will increase, and the variance are the control of the convergence rate of stochastic gradient, so we are in a big problem. It's not a good solution to the safety problem. So how we ensure that reinforcement learning is safe? How we ensure that the output of the learning process is safe? And our idea is to decompose the problem into a composition of two functions. So we want to learn a policy pi from the state space into the action space. What we are going to do is we are going to decompose pi into two components. One component, pi theta with a superscript of d, is responsible for desires, and it is being learned. So we define a set of desires, what we want to do, what we wish to have, okay? And it is responsible for the comfort of the driving and for making progress. Another component, pi of t, pi of trajectory, is we take the desires and we translate them to an actual trajectory of how we are going to drive, okay? And we do it without learning and by making hard constraints for this optimization problem that solves the trajectory problem, we make hard constraints on safety. So if you are going to drive according to this trajectory without good desires, then you are not going to make any accident, but it will not be nice. So the car can brake very, very strongly, and it can just stop in place. And it can do things which are not comfort, but they will be very, very safe. Now the whole system will combine desires that the role of the desires is to ensure that we almost never arrive to the hard constraints on safety. But once in 10 to the -8 times we may hit a hard constraint, and in this case the hard constraint will prevent an accident. It will not be nice, but we will make no accidents. So what are these desires? So for example, a desires would be, I want to overtake into the gap between these two cars. So the red car would want to arrive to the position between these two white cars. Another type of a desire is to decide on every other car if to give way to this car or to take way from this car. And this is how we negotiate our way in a very crowded and unstructured scenes. Other desires are having a semantic meaning for pedestrians, like for these two pedestrians, we just want to have an offset, and for this pedestrian here, he is likely to cross the road, so we want to have a different semantic meaning to this agent. So I will show you some result of this safe driving. Now the agent is the red car. This is the road simulation of the road from Shai to Jerusalem, and often there is a slow vehicle on the right lane and very high-speed vehicles on the left lane, and we need to overtake. So what you see here is that the car learned to negotiate its way. I will show it again. So at the beginning, it pushes a little bit its way to try to negotiate with the other drivers. It sees that it doesn't get the right of way. It tries again. Now the car is speeding up, so it backs off, and finally it is in a good position to merge into the traffic and make the overtake. Another simulation, Arc de Triomphe in Paris. So now the agent is this bus, and it needs to arrive to the other side. So the desires are give way and take way from other cars, and it's slowly but fiercely, and it finds its way to the other side and succeed in making this progress and going to the other side. And all of this is done by enforcing safety using hard constraints. Okay, so how much time do I have? 10 minutes. Okay, so intermediate summary, we discussed reinforcement learning without Markov assumption, which is essential for driving policy because there are many other agents on the road. And we discussed how to enforce safety and constraints into reinforcement learning. All of this is nice, but to make it really work, we have some additional challenges. One of them is chaos of dimensionality, and we tackle it by semantic abstraction. We decompose the driving policy function into a set of semantically meaningful components using an options graph. And then the output goes to continuous trajectory planner. There is also a component of enhanced simulation. We use self-play, so we start with very naive agents, and then we train one agent, and then we get more interesting behavior, and then we make the other agents behave like this agent and continue this loop. So we get more and more complicated behavior of other agents, and it's very nice to see how this gradual improvement makes very complicated behavior of the flock. We also leverage human data. So this option graph, the idea is very simple. We decompose the problem into a set of semantically meaningful and simple decisions. So if we decided to overtake, then we go to select the gap, which are the two cars that we are going to fit between, and then we need to find if there is a gap, or to wait, maybe there is no gap, and if we are waiting, we can push our way or make room, so have enough distance to the preceding car in order that we can accelerate into a gap, or we can stay in place and wait for the next iteration. So decomposing the problem into this graph help us to learn every component of the graph much faster, and the overall system is more transparent, and we can understand what's going on in the...
Isn't it equivalent to some sort of Markovian assumption?
No, there are no...
The actions, not of the states.
There is Markovian assumption, what I called agnostic Markovian assumption, because we make our decisions, the choice of our decisions is only based on the state. Okay, so we make, this is the only assumption that we make. This is a design choice. In the same, it's not assumptions on the word, it's assumption on the hypothesis class that we're using to use in the same way that you choose to deep network of a specific architecture. It's not assumption on the word, it's assumption on what you are going to use. So again, here, it's assumption of how we make our decisions. Okay, so to sum up, driving in realistic, dense traffic scenes calls for machine learning. We need to understand the intentions of other agents. We need to negotiate with other drivers. We need to balance the trade-off between defensive and aggressive behavior. We need to figure out the rules of breaking the rules and to deal with uncertainty. And the main component of our approach is first to learn while ensuring safety. To learn without making too harsh assumptions on the word, the agnostic reinforcement learning without making Markovian assumption on the word. We decompose the decision-making process into an option graph, which gives us a semantic abstraction for the decision-making. We enhance the simulation using self-play, and we leverage human data for initializing the learning process. Thank you.